Very good morning to another person here. Myself M.Anandraj, working as an Assistant Professor in the Department of Computer Science Engineering in Mahindra College of Engineering, Salem. Today we are going to look at the topic deterministic finite automata and non-deterministic finite automata, which comes under a subject theory of computation. Before getting into the topic, we need to know about the prerequisite. So, the hierarchy of languages. Theory of computation is study about the laws of computation, that is impossibilities of a computer which can be studied through the help of an automata. Automata is that a self-acting machine. It is a plural form of automaton. There are various kinds of an automata. Automata is also a mathematical abstract model which has four kinds. One is finite automata, linear bounded automata, push down automata, and another one is the Turing machines. Every automata has some various languages. A finite automata which consists with a regular language. Finite automata has a limited amount of memory, so only it is said to be a finite automata. That is the initialized automata which has been found. Later on, we have push down automata. That is comes with context-free languages. We use an additional preferences of a memory which is called as a stack. So it can be the additional process of storage can be stored using help of a stack. Then a linear bounded automata which has a recursive language. Finally, the Turing machine, which nowadays are called as a modern computer. So Turing machine which has a recursive enumerable language which has some decision authorities. So these are some prerequisites of a DFA and NFA. So from four kind of automata, we now look upon finite automata. Finite automata is a automata which is self-acting machine with a finite amount of memory. Furtherly, it has been partitioned into two types of an automata. One is a deterministic finite automata and non-deterministic. Deterministic is that single path. So when we define an automata, it has three variations. One is it can be determined with the help of a transition diagram and a table and a transition function. So automata which looks at it has input tape. Here input tape is being represented with a string placed on the tape, that is 0, 1, 1, 0, 0. Also it has some finite control. That finite control will manage and manipulate the input strings. It is a one-way read-only tape head. The arrow mark is said to be in a tape head or a pointer which helps to read a string on the input tape which has been presented. So the finite control has a finite number of states and transition rules among the string. Transition rules that it will be providing a language to the strings based. Suppose in this string starts with 0 is represented as a 0, 1, 1, 0, 0 string. So that is a rule. String should be starts with 0. So the finite control has a program containing the position of read head. The current symbol has been scanned and pointed into the current state. So the various number of states is being available in a finite control, which can be represented with the help of Q0, Q1, Q2 basically, or we can use capital A, B, C, such a non-terminal strings. So this is the basic structure of a finite automata. In this, a deterministic finite automata is that only it moves with the single transmission. From one state, the input will be moved to the another state. It will not be pointed to the two or more number of states. It will be pointed to only a single state. That is said to be a deterministic finite automata. So these are the formal definition of a DFA. It consists with the 5 tuples represented with M is equal to Q summation del Q0 and F. Whereas Q is a finite set of states. In input alphabet, it presented with a finite set of states, that is Q0, Q1, Q2, Q3, and a summation. Summation is a finite input alphabet. It has been presented with a string called input alphabets, which means with the help of a lowercase letters, maybe A, B, C, like that. If you want to represent an example, apple is a string. It has a input character with A, P, comma, P, comma, L, comma, E. So that all will be called as an input alphabet. So the finite amount of input alphabet is represented with the summation symbol. Then we have a Q naught, that is the initial or starting state, which comes under a capital Q, finite set of states. So finite set of states has many number of states. So in that we usually represent with the Q naught as a starting state. Then F is a set of final or accepting states, which is also a subset of a Q. So F is the finite state. In this starting state Q naught, which is represented with the arrowhead, and final state with a double circle, enclosed with a double circle. Another one is del. Del is said to be a transition function, which has a formula that Q cross summation tends to capital Q. That is, from one state, if we give the input, it will be moved to the another state. So del is defined for any Q in a capital Q and S in a input alphabet, and is equal to some other state called a Q dash. Q could be Q dash is equal to Q. So that what it represents here. So transition function rule, which is Q cross summation tends to capital Q. So all this deterministic finite automata and non-deterministic finite automata, which prove with the help of an inductive proof that a machine correctly accepts a string at least 2 C's. So in this transition diagram is shown here, Q0, Q1 and Q2. From Q0 to Q1 it has been pointed with a state called C, and from Q1 to Q2 it has been pointed with a state called C. So 2 C's is being moved from a starting state to a final state. So A and B are the extra strings which can be moved to Q0, Q1 and Q2. From leniently, we have to show that at least 2 C's should be passed from starting state to final state. Here Q0 is a starting state which is represented with the arrowhead, and Q2 is a final state which enclosed with a double circle, so that from starting state to final state it has at least 2 C's. So this can be proved in basis of inductive proof. With the base, we take the length of the x is equal to 0, so that if length of x is equal to 0, the string has an empty string. So the Q0 state is a starting state where the string will be rejected. In this case, a transition diagram, a diagram will reject the strings. In inductive hypothesis, we take some integer as a extra values. So if we put a k is equal to 1 or 2 more than 0 values, then only we can able to check the string whether which will be accepted or rejected. So from a state Q0, starting from state Q0, C should be moved to Q1, and Q1 whereas C should be moved to Q2. So that 2 C's, at least 2 C's has been presented in a transition diagram. In that cases, if Q2 accepts 2 C's, then it will be accepted. If a Q1 accepted only 1 C, so if only 1 C is being present from Q0 to Q1, then the state is said to be an rejected state. So this can be proved in case of inductive proof. This is said to be a principle of mathematical induction. Let us see with example 1. In this diagram, transition diagram has been shown here from a state Q0 and Q1. Q0 itself is act as a start state and also a final state. In this diagram represents languages at even number of zeros. So from a Q0, if we have an input 0, it will be moved to Q1. From a Q1, if we have an input 0, it will be again moved to the Q0. So consider as a string 10011. It has an even number of zeros. That is 2 zeros being presented in the string. So from Q0 to 1, it moves to Q0. Q0 to 0, it moves to Q1. Q1 to 0, it again moves to Q0. Q0 to 1, it moves to Q0, and Q0 to 1, it again moves to Q0. So it comes to final state Q0. So the string is said to be accepted. If some other string, if we consider only a 0, 1, 1, in that case a string will be rejected. For example, if 0, 1, 1, from Q0 to 0 it will move to Q1, from Q1 to 1 it moves to Q1, and again 1 if we put, it also moves to Q1. So Q1 is not a final state. So in that case a string will be gets rejected. So this is about DFA accepts a string containing even number of zeros, including the null string over a sigma 0, 1. That is the input which presents with a 0 and 1. So this is a transition diagram and table. Here capital Q is represented with Q0, Q1. So Q has number of states called Q0 and Q1. Summation has the input alphabets 0, 1. Here start state is Q0 and the final state is also F, represented as F, is said to be Q0. It is been enclosed with a double circle. So transition table is given below with rows consist with the states Q0 and Q1, and input is represented in a column as a 0 and 1. From Q0 0, if we give as input, it moves to Q1. From Q0 1 as an input, we will be moved to a Q0. So this is an example 2. Here it is a transition diagram for 2 C's, at least 2 C's. So in the first case, we take a string A, C, 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 B. In that case, a string is said to be accepted. In A, C, it has only one C. So in the second case, a string is to be rejected in the given transition diagram. So this is how we prove with the transition diagram. So these are called a computational process of an automata. So these are some of the examples. Now let us look upon non-deterministic finite automata. So non-deterministic finite automata has also a 5 tuples, the same as the DFA, whereas Q is said to be a finite set of states, summation is said to be in finite input alphabet, Q0 is the initial or starting state in Q, F is a set of final state and accepting state, which is subset of Q. Del is a transition function. Here comes with only differences between DFA and NFA is that transition function del. Q cross summation tends to Q in case of DFA, whereas in case of NFA, here it is represented with the red color 2 to the power of Q. That is when we give an input to one state, it will be moved to the multiple number of states. That is the only difference between deterministic and non-deterministic finite automata. For example, if we give a input state, see, from Q0 to input as 0, we will be moving to Q0 and also to Q1. In first case, it is said to be a deterministic non-deterministic finite automata. Since we give an input as 0, but it moves to the 2 states. So this kind of an automata is said to be a non-deterministic finite automata. Notes that a string is said to be accepted if there exists path from Q0 to some state of final state. A string is rejected if there exists no path to the state in final state. So if a string exists between a starting state to final state, then a string is said to be an accepted. If it has no path from a starting state to a final state, then a string is said to be a rejected case. So the language accepted by NFA is set of all accepted string. And we can have a question that how does an NFA find the correct or accepting path for the given string? NFA is a non-initiative computing model. You may use a concept of a backtracking here to find if there is existing path to the final state in the following slide. So we'll be looking at the slide. In this case, determining if a given NFA accepts the given string 001 can be done algorithmically. For example, see the below diagram from Q0, Q3 and Q4. Here comes 2 final states, one is Q4 and Q2. We need to know whether string 001 has been accepted by this diagram, transition diagram. So In first case, we need to represent from Q0 where all the strings are moving. So we have determined with the help of a transition diagram through a various path. In this case, from a state Q0, then if we give an input 0, it moves to the Q0. Then again, if we give an input 0, it again moves to the Q0. If again we give an input 1, it moves to the Q0. In this case, the string will be gets rejected, since Q0 is not a final state. So we can accomplish a same string in many deterministic path, but we need to accommodate a string in from a starting state, and path should end with the final state. So in this third branch, that is Q0 to given input with 0 moves to Q3, and Q3 with the input 0 we move to Q4, and from Q4 if we give an input 1, it moves to Q4. Here Q4 is said to be an final state, so that the string is said to be accepted. So here we has some examples has been given here. We can be see in the next session. So thank you so much for watching my video. Thank you.